Hello, in the previous video we were considering velocity, and I said in this video we are going to consider centripetal acceleration. So let's get into that one. This section is very important as well, because when you get to do Doppler effect and all when considering stars and all of those, these circular motion concepts are very important. They are very fundamental, even when you're doing gravitation. That's why I had to do it as a second topic. So now, centripetal acceleration. Let's consider an object moving in a circle center, or consider the object is at A, and after time delta t, it's now at B. The radius has gone through an angle theta. No, let's say delta theta to make it small. Just a small angle delta theta to make it. So let's consider velocities. I think in the previous video I forgot to mention something. When we calculated this velocity, let me look for the slide where we calculated the velocity. This velocity here, it is a tangential velocity. It is velocity that is tangent to the circle at that point. That is this v. W is angular velocity, yes, but the v is tangential to the circle at that point. At B, this one will be VB. That is the velocity at B facing in that direction. And here it will be tangential to the circle at point A. So this is velocity A. That's what we are going to use right now. Because you know acceleration is the rate of change of velocity. So if you can get the velocity and get that changes, then you can get our acceleration. So at this point here, velocity will be like this, tangential to the circle in this direction. And at B, velocity at B, I'm going to denote it VB. It will be in that direction. So that is, this one is VA, that one is VB. So now, after a short time delta t, the object is now at B, and its velocity is VB, and is in the direction of this tangent BD. Let me call this tangent BD, and let me call this tangent here AC. Let me call the tangent AC for easy reference. So this tangent here that is representing VA is AC, and this tangent here is BD is representing velocity at point B. So different directions. Can you see? AC is VA is facing a different direction from VB, and we know that velocity is magnitude and direction. Whenever any one of those two factors changes, it means there is acceleration. So since the direction has changed, it means there is this object is accelerated from A to point B. There's acceleration. Maybe the magnitude might be the magnitude of the velocities might be the same, but due to the change of direction, then this object is accelerated. That's the centripetal acceleration that we're trying to figure out. So now, looking at the velocity change, because you know acceleration, as we know, acceleration from kinematics, acceleration is equal to change of velocity over change in time. So let's figure out the change in velocity from point A to point B. Let's figure out what that velocity change is. Okay, let me do this. Okay, in geometry. In geometry, there is a geometrical proof for this, but it would take time for us to prove it. But let's extend this tangent to meet the tangent for BD. Where it meets the tangent BD, it makes an angle equal to delta theta, the same angle that is at the center. If BD was here, or if let me say point C is there, therefore our VC will be facing up like that. If we extend the tangent to meet AC, it makes an angle of 90 degrees, and this radius would also make an angle of 90 degrees to where it started. So basically, when we extend the tangent of BD, to meet this AC, it will make an angle of delta t, the same angle that is at the center like that. So now, let's form a geometrical shape of what is happening here. We know that our delta V is equal to VB minus VA. obviously v final minus v initial. That is what? That is the change in velocity. But we can rewrite this as vb plus minus va. Plus minus va. And what is minus va? In vectors, when you do a negative, you basically mean in the other direction, in the opposite direction. So can you see va is facing due east? So when you put a negative, it will now face due west. It will face due west like this. North, south, east, west. So okay, due right. This one is facing due right. So minus va will face what? Face due left in this direction. So it will be vb like vb in this direction plus va. So let's do that. It will be vb like this, because that is what vb, that's how you add vectors, you maintain the direction. But we said minus va was initially like this, so we are going to add the plus. And you know, you add the tail to the head of what? Of the previous vector. The previous vector was vb, so to this we are going to add what? The tail of va. But va now is facing the other direction. It's not facing this right direction now, it's facing left. So va will be like this. So this one will be va. So this one is negative va. So this is vb and this one is va. And we know that when we are adding vectors, to get the overall effect of the resultant of addition of vectors, you just trace out from the beginning to the end of the trail. So vb plus minus va, we land at this point, and the resultant of this is this. This is the change. This is the change in velocity. That is the change. The resultant will be the change in the vectors. So if we had many vectors like this, lined up like that, this is the end point, this is the starting point. The change would have been the straight line that links the initial point to the final point. That would have been the change. Here the change links the initial point to the final point as we go through, or you can, as you go through like this, vb plus minus va, like that. So this is what? This is delta v. So now let's label our diagram p, q, and we're going to call this point r. So therefore my delta v is equal to vector pr. As you can see, this is equal to vector pr. When delta t, now considering when the time is very, very small, then this angle delta theta is also small, because we might be considering when b is very close to what? To a. B will be very close to a because it hasn't moved much because the time is small. So in that case, the angle PQR, which is small, will be equal to angle delta t. These proofs are from, you can get these proofs from geometry. When you consider just looking at this diagram here, can you see that this is equal to what? To our PB, right? This is equal to our PQ. This is equal to our PQ vector. This part here is equal to our PQ vector, and this angle is what? This angle here, it's equal to theta. So when we do, this one is VA. When you do minus VA, we can transpose minus VA and put it on this part here, because this will be equal to minus VA. It will be equal to minus VA, right? Just facing the opposite direction, equal to VA but facing the opposite direction. And you know those alternating angles from geometry. So this angle here is equal to what? To delta theta. That angle is equal to delta theta. And when we take that shape, that is VA and minus VB, that is exactly the shape that we came up with here. That is exactly the shape here, VB and minus VA. So this angle here is equal to what? To delta theta, as I said. So now this delta theta will be small. PR then points to the center of the circle. Can you see that PR, the way, if you are to take this shape and put it on top there, it will be VB and our VA will be facing like this. And our PR, if this one was drawn to scale, our PR will be something like this. It will be a vector on this side like this, and it's facing the center. Even B, when it was here, PR will always face the center. I think you can do this, draw different positions of B, and try to get the PR vector. When you get the PR vector, it's always facing the center. It's always facing the center, and therefore, since PR is the change of velocity, we know that acceleration occurs in the same direction as what? Direction as the change of velocity. Acceleration occurs in the same direction as what? As the change of velocity. So our change of velocity is facing the center. Therefore, our acceleration is what? Our acceleration is towards the center. It's always towards the center. When it's what? When the object is moving in a circle. When the object is moving in a circle, our acceleration is always towards the center. Hence the name centripetal acceleration. Centripetal encompassing the name center seeking. It's always seeking the center. It's centripetal acceleration. Therefore, acceleration, okay, is towards the center. But let's get its magnitude. Let's get its magnitude. We know that acceleration is equal to velocity change over what? Over time. We know that acceleration is equal to velocity change over time. This is equal to PR over delta t. That's what we know. It's equal to PR over delta t. This is the wrong slide. Sorry, wrong slide. Where is the? Let me. I want to take the original slide that we had. Our acceleration is going to be p, because here we said what? PR is equal to. And because we said PR is equal to what? Is equal to what do you call this? We said PR is equal to delta V. So here we are going to have our delta V is equal to PR over delta T. But PR is that vector, and we can use that S is equal to R theta thing that we used we used before. So here we want the length of PR. What is the length of PR? We know that this length, the length of PQ is equal to just velocity. The velocity the object is moving at. I said the magnitude is the same for VA and VB. The magnitude was the same. Magnitude was equal to V, but the direction was changing since it's what? Moving in a circle. So now we know that the length of this is V and the length of this is V. So we can use our S equal to R theta. In this case, our theta is going to be for us to calculate the length of this part. So when you use R, our R is V because that is the what? That is going to be the length of this part, and our theta is just going to be delta T. So let's put that in our equation. So this will be equal to, this is equal to V dot delta theta over delta T. But that we can separate as V delta T over delta like that. So our acceleration is equal to, what is delta T over okay, now I'm going to do a bit of calculus. So our acceleration, because now we're considering a small time, a small what? Change in time. But let that change in time approach 0 for us to get an accurate value. Therefore, A is equal to the limit as delta T approaches 0 of V over T like this. V is a constant because we said it's a constant, so it goes out of the limit sign. So this is equal to V limit as delta T approaches 0 of del theta del T like that. So this one will be equal to V. The limit is delta T approaches 0. These ones become derivatives. They become derivatives. So this is V times d theta over dt. D theta over dt. I think we've seen this before, what d theta over dt is. If you remember well, when we're doing angular velocity, here when we're doing what? When we started our circular motion, we say W is equal to d theta over dt. So now in our centripetal acceleration, this becomes equal to V dot W, because this part here is angular velocity. So we have a new equation, A equal to V dot W, like this. A is equal to V dot W. And using the other equations, the other equation that we had was V is equal to RW, you can also prove that A is equal to v squared over r by replacing w by v over r, because when you change the subject of the formula of this to make it to angular velocity, you get v, and then replacing here you get v over r, and replacing this you get this new equation, or a is equal to rw squared by the same method. Here replace v instead of w. Replace v. When you replace v, it's going to be rw times w, which is wr squared. These formulae are very important when you're calculating acceleration. In the next video, we are just going to do, I think it will just be 2 minutes to do centripetal force, because wherever there's an acceleration, there's going to be force according to Newton's second law of motion. So let's get into that one in the next video.